Hey, so in our last video, we talked about some of the basics of circular motion. We talked about, the tangential velocity. We talked about the centripetal acceleration. And in particular here, we talked about the centripetal force. And, some of the more interesting applications of this stuff has to do with the motions of planets and moons and things in outer space, spaceships, satellites, things like that. And for these kinds of objects that are moving in space like this, that centripetal force that maintains their circular path is usually provided by gravity, right? We call it the gravitational force. And so today, I want to talk a little bit about gravitational force. And our target is to be able to describe circular motion by using the law of gravitation. So let's go ahead and let's talk about some of those things. So like I just mentioned, when we talk about circular motion, some of the more interesting applications, at least interesting to me, are objects moving in outer space. Whether we want to talk about planets or moons or asteroids or comets or spaceships or space stations or satellites or, lots of different things moving in outer space, these objects move in what's called an orbit. An orbit is an example of circular motion, right? For orbiting objects, that centripetal force is provided by gravity. Now, a lot of times, I've been teaching science a long time, and a misconception that students often bring to physics class is that there's no gravity in outer space. Okay. If there were no gravity in outer space, things wouldn't be able to maintain a circular motion because it's that gravity that holds them in a circular motion. In fact, after we learn this today, you can do the calculation for yourself. A lot of people don't believe that the astronauts up on the space station feel about the same pull from Earth's gravity as you do here on the surface. And oftentimes people don't believe that because you look at video of astronauts in space and they are not standing on the floor. They're just kind of floating around in their spaceship or their space station, or they've got things around them that are floating, and they say, oh, there must be no gravity. Well, there's gravity. Then they ask, why do these things float? If there's gravity there, if gravity is really not that much less on the space station, then why are things floating? And the answer is that they're not floating, they're falling, right? And that's kind of what an orbit is. An orbit isn't so much, the things there aren't so much floating as they're falling. They're falling along a very special path, okay? Let's talk a little bit about what an orbit is and what it looks like. I have a little graphic I'm going to put up here, and this is kind of like a really classic way to explain an orbit. Okay, think about it like this. Picture you have a giant cannon on top of a huge mountain. You might be able to see in the picture there, a giant cannon on top of a huge mountain. And our cannon is going to fire a cannonball. And let's say it fires the cannonball just not very hard, at a low speed. What's going to happen to that cannonball? That cannonball, well, it's going to move out tangentially from where it started, but gravity's quickly going to pull it down to the ground. So you're going to get this curved path that goes from the cannon, just kind of bloop right down to the ground. All right, and you can see that in the graphic. It's labeled A in the graphic. What's going to happen if we fire that cannonball a little bit faster? If we fire it a little bit faster, it's still kind of the same thing is going to happen. The cannonball is going to move out kind of tangentially, and gravity is still going to pull it down towards the ground, and it'll go, a little bit further if we fire it a little bit faster, right? And you can see that scenario there labeled as B. But now think, could we fire that cannonball with enough speed that rather than, having gravity pull it to the ground, gravity's still going to pull it towards the ground, but could we fire it fast enough that it misses the ground entirely? So it misses the ground entirely and comes right back around to the backside of the cannon, right? And that situation is labeled as C in the diagram there. And that is what you call a circular orbit. So you fire your cannonball with just the right speed, it'll completely miss the ground, come around all the way around the planet, and come right back to the back of the cannon, right? There are other kinds of orbits that are not as circular. You can see labeled as D. This is a more elliptical orbit. That one will also come around and hit the back of the cannon, but that's fired a little bit faster than C. And then there are other paths that it can take. You can fire that cannonball, with an extreme speed and get the situation labeled as E. In this case, that cannonball is going to escape the planet's gravity and, fly off into space. But in any one of these cases, gravity is pulling down on the ball. It's pulling the ball towards, the Earth. Okay, so because gravity is so important to these kinds of applications, let's talk a little bit about how to calculate the force of gravity. It's really not that tough of a thing to do. Remember, one thing to remember about gravity before we get to that, okay? Remember the third law of motion is for every action, there's an equal and opposite reaction. This is a common misunderstanding of gravity. Oftentimes people think of gravity as, like the planet pulling on something. But really what gravity is two objects pulling on each other. Remember the third law of motion, for every action there's an equal and opposite reaction. So whatever force, let's say the Earth pulls on you with, you pull on the planet with an equal amount of force, right? So both objects involved experience the same force, just in opposite directions. Okay, so we can calculate the force of gravity. It's pretty simple. We have an equation here. This is called Newton's law of universal gravitation, and it says that the force of gravity is equal to G, capital G, not lowercase g. This is not lowercase g. This is capital G. We'll talk about it in a second. It says G times m1 times m2 divided by r squared. Now let's talk about what some of the terms in that equation are. Fg is obviously the force of gravity. Okay, we've talked about that before, measured in newtons. The two m's are the two masses of the two objects involved, right? So if there's two different objects involved, you got two different masses. Could you have gravity? Could you have a force of gravity with only one object involved? No, because you need two objects. Gravity exists between two objects, right? So M1 and M2 are the two different masses of your two different objects. It doesn't matter which is which. And R is the distance between their centers. And this becomes very important when we start talking about planets, okay? R, the radius of the circular path, right? R is the distance between the centers of the two objects. Sometimes people get confused, especially when we're talking about planets. They'll measure a distance from the surface of the planet, but that's not what this is. This is from the distance from the center of the planet. If you think about, if it were the distance from the surface, then with you standing on the surface of the Earth, your distance from the surface would be 0. And if you put 0 into this equation, then you got a 0 in the denominator, which would mean the force would go to infinity. So then standing on the surface of the planet, you would experience an infinite amount of force, and it would just crush you under your own weight, right? But that doesn't happen, so that's obviously not the case. So R is the distance between the centers of the objects, not the surfaces of the objects. Now let's go back and let's talk about that G for a minute here. Okay, G is a constant. It's what's called the gravitational constant. This is kind of like a measurement of how strong gravity is in general. There are throughout nature a few of these constants, and these constants are really just a number that describes something about nature. And this capital G is called the gravitational constant. And it is equal to 6.673 times 10 to the negative 11th Newton meters squared per kilogram squared. It's a weird unit, I know. But, we just need to know the number there, 6.673 times 10 to the negative 11th. The number will appear on your assignment, so I don't expect you to remember it. So we can calculate the force of gravity. It's really not that tough. All we got to do is take that G times the two masses divided by the distance between the object's centers squared. So it's really not that tough. I have on occasion had students get confused because the G in the equation is in front of the fraction. Most of you guys are good at math. You understand that G could be placed in the numerator of the fraction. We can make it look like this, or this, somewhere over there, right? Physicists like to put the constants in front of the fraction to kind of say, hey, this is a constant, right? But you can think of it as being in the numerator. It's kind of the same thing there. Okay, let's go look at, one more thing to point out here. Notice there's no limit there to the mass of the objects, right? Any two objects that have mass are going to experience a force of gravity between them. You could calculate the force of gravity between two pencils in the classroom. It exists. It's not going to be a very big number. It's going to be a very, very small number, but it exists, right? You could calculate the force of gravity between two trees on opposite sides of the planet. It's not going to be very much, but it exists. You could calculate it, right? So that said, let's go ahead and let's take a look at an example of a problem and see how to use this. Having a look at the example here, it says, find the distance between a 0.300 kilogram billiard ball and a 0.400 kilogram billiard ball if the magnitude of the gravitational force between them is 8.92 times 10 to the negative 11th newtons. Notice how small that force is, 10 to the negative 11th. That's tiny. Okay, so I have my law of gravitation here, and I know G is 6.673 times 10 to the negative 11th Newton meter squared per kilogram squared. Now the problem tells me that I have two masses here. The first one is 0.300 kilograms, and the second one is 0.400 kilograms. Doesn't matter which is which. You could call this one M1 and this one M2. Work out the same. And then it tells me that the force of gravity is this tiny amount. It says 8.92 times 10 to the negative 11th newtons. Okay, and it wants to know what's the distance between them. So it's asking me to find R. Let's go ahead and put the numbers in there and see what this works out to. So FG is this one. I'm gonna write down here so I got 8. That's a terrible 8. 8.92 times 10 to the negative 11th, and that's going to equal G, which is 6.673 times 10 to the negative 11th, times M1, which is 0.300, times M2, which is 0.400. All of that is over R squared, and that's what we're looking for, R squared. Okay, so the first thing I'm going to do to solve this is I'm going to take my R squared and I'm going to multiply it to this side. And at the same time, I'm going to take this number and divide it over to this side. So then I will end up with R squared equals 6.673 times 10 to the negative 11th times 0.300 times 0.400 divided by 8.92 times 10 to the negative 11th. Now, you could at this point just plug all that into a calculator and be just fine. I am going to cancel these 10 to the minus 11ths because they're the same. And then I'm going to punch all that into a calculator. If you didn't catch that you can calculate that, it's okay. You can still punch it in the calculator and get the same thing. So I have 6.673 times 0.3 times 0.4 divided by 8.92. And so on this side, I've still got R squared. And on the other side, I've got 0. Let's see, how many significant figures are we dealing with here? 3, 0.0898. And then we'll go ahead and take the square root and see what the answer there is. Square root of 0.0898. And I get about 0.30 be 0, 0. And being a distance there, that'll be in meters. Okay. So, and we can, that might be a convenient number to put in centimeters. So we'll move the decimal point over a couple of places. That's the same as 30.0 centimeters. If you left it in meters, that's perfectly okay. Okay, so there's a little bit about the law of gravitation. We talked about the law of gravitation, how to solve problems with it. We talked about orbits and stuff along those lines. In the next few lessons, we'll go ahead. We're going to talk about the laws of planetary motion. So we'll talk more about objects moving in space and such. So hopefully that lesson helps us to be able to describe the motion of objects in circular motion using the law of gravitation. So until next time, take it easy.